Dear students, today we'll see a few multiple choice questions on the topic of PLL, that is phase lock loop, and a clipper and clamper circuits under the subject analog electronic circuits. So let's start with the first question, question number 81. Free running multivibrator is also called as what? The options are stable multivibrator, voltage control oscillator, square wave oscillator, pulse stretcher. Now, if you remember a free running multivibrator, now that multivibrator was having external components like a capacitor and resistor, and then there was a control voltage input. Now, as we give the control voltage input, the output frequency will deviate from one point to another. The output frequency can change depending upon the input control voltage. That was the a concept what we saw in free running multivibrator. So if the output frequency is varying depending upon input control voltage, then it comes under the concept of voltage control oscillator, because the output frequency are varying by varying the input voltage. So option B will be the right answer here, voltage control oscillator. Free running multivibrator is also called as voltage control oscillator. So here you can see the explanation. Free running multivibrator operates at a frequency which is determined by an external tuning capacitor and a resistor. On applying a DC control voltage, the frequency can be shifted on either sides. This frequency deviation is directly proportional to the DC control voltage, and hence it is called as voltage controlled oscillator. So here the option B will be the right answer, voltage controlled oscillator. Then we'll go to the next question, question number 82. The output voltage of phase detector. So the options here are phase voltage, free running voltage, error voltage, and none of the mentioned. Now, if you see the output voltage of a phase detector, now input to the phase detectors will be your desired frequency and the feedback frequency. So here if you see the input in your PLL or diagram, if you see the input to the phase detector, if you're having a phase detector as your unit, so in that if you see the input, one will be the input frequency what you're going to give as desired input, and one will come as a feedback from the output. This will be the feedback, and the output of phase detector will be a voltage which depends upon the difference between the two inputs, and that voltage is called as error voltage. That voltage is called as error voltage. So here the option number 3 will be the right answer, that is option C will be the right answer, error voltage. So here you can have the explanation. The phase detector compares the input frequency with the feedback frequency and produces output DC voltage called as error voltage. So option C, error voltage, is the right answer. Then we'll go to the next question, question number 83. At which state the phase lock loop tracks any change in input frequency? Now here the options are free running state, capture state, and phase lock state. Now these three states are the states of PLL in which it is going to work. So before you apply the input, it is free running state. After you apply the input, it is a capture state. And after you hunt and lock to a particular frequency, it is phase lock state. So the question asked over here is, at which state the phase lock loop, that is PLL, tracks any change in input frequency. So the tracking of any change in input frequency and then locking to a frequency as desired, that process comes under phase locked state. That is option C will be the right answer here, phase locked state. So here you can see the explanation. In the phase locked, the output frequency is exactly same as the input signal frequency. So the circuit tracks any change in the input frequency through its repetitive action. So here you can see option C will be the right answer. It is the state where you are going to track any change in input frequency. The PLL is going to track any change in the input frequency. Then we'll go to question number 84. Match the list 1 with list 2, which represents 3 stages of phase lock loop. So we know that phase lock loop works in three stages. And what are the three stages? The three stages are free running state, second stage is capture mode, and third stage is phase lock state. Okay. So here, if you see list one, number one says that before input frequency is applied. Okay, so before input frequency is applied, it is free running state. The PLL is in free running state. When the input frequency is applied, then it is in capture mode. The PLL is in capture mode. After input frequency is applied, the PLL is in phase locked mode. It is in phase lock mode. So then what are the options? For number one in list one, we have option two in the list two. Number two, we have option three. And number three, we have option one. So here, if you see the combinations in the answer, for number one, the second option of list two, for number two, the third option, and the number three, the first option, that means option A is the right answer. So option A is the correct combination of list one and list two. So here you can have an explanation of this. Before the input is applied, the PLL, that is phase lock loop, is in a free running state. This you have to remember for any other question asked on this topic. Once the input frequency is applied, the VCO, that is voltage control oscillator frequency, start to change and the PLL is set to be in capture mode. When the voltage control oscillator frequency continues to change until it is equal to the input frequency, the PLL is set to be phase lock state. So it is the first one is free running state, second one is the capture mode, and third one is the phase lock state. So here you can see that the option one, that is option A, a combination shown in the option A of list one and list two is the right answer as we have told earlier. Then we'll go to the next question, question number 85. What is the function of low pass filter in phase lock loop? Okay, so if you remember the block diagram of phase lock loop, there is a low pass filter used in a PLL block diagram. Now for what it is used? Here options given are it improves low frequency noise, it removes high frequency noise, it tracks the voltage changes, it changes the input frequency. So low pass filter is one which will remove high frequencies. It will not allow high frequencies to pass. That means option B is the right answer. It removes high frequency noise. So here if you see the explanation, the output voltage of a phase detector is a DC voltage and is often referred to as error voltage. This output is applied to a low pass filter which removes the high frequency noise and produces a DC level. So here you can see that option B is the right answer. Low pass filter in PLL removes high frequency noise. Then we'll go to question number 86. What is the need to generate a corrective control voltage? Now, why we should have a corrective control voltage so that the error voltage is correct and then the output frequency is correct in PLL working. So the options given here are to maintain the lock, that is the locking frequency, to track the frequency change, to shift the voltage control oscillator frequency. Now all these 3 points are the process of PLL and all these 3 points need a corrective control voltage. So what is the need to generate the corrective control voltage is to have to maintain the lock, to track the frequency change, to shift the voltage control oscillator frequency, and the option D, that is all of the above mentioned. So here all of the above mentioned reasons are correct. So option D will be the answer here, all of the mentioned above reasons. So here in explanation you can see the output frequency F0 of voltage control oscillator is identical to input frequency Fs except for a finite phase difference phi, which generates a corrective control voltage to shift voltage control oscillator frequency from F0 to Fs, thereby maintains the lock once locked, and PLL tracks the frequency changes of the input signal. This is the way it is going to work. So here the option D, that is all the above reasons are true. What is the need to generate a corrective control voltage? Then question number 87. At what range the PLL can maintain the lock in the circuit? So options are lock-in range, input range, feedback loop range, and none of the above mentioned. So here the concept is called as lock-in range. At what range the PLL can maintain the lock in the circuit? That range is called as lock-in range. Okay. So here you can see the explanation. The change in frequency of the incoming signal can be tracked when the PLL is locked. So the range of frequencies over which PLL maintains the lock with the incoming signal is called as the lock-in range. So here option A will be the right answer, as we have told earlier, lock-in range. Then question number 88. In the locked state of PLL, the phase error between the input and output is dash. Now we know that whenever the PLL comes to that locked state, that time the input and output frequency will be almost equal to each other. And when they're equal to each other, the phase error between input and the feedback, okay, that has to be the minimum. So we have minimum error. So here in the options, if you see, option C is minimum. That is the right answer, because in the locked state of PLL, the phase error between the input and output is minimum. Okay, so it should be minimum because it's in lock state and the output is equal to your desired input. So inputs and outputs are same. So in that case, it is locked. Therefore, the error will be minimum or there will be no error at all. So it is a minimum error. So minimum is the right answer here. Then we'll go to question number 89. In a communication circuits, PLL, that is phase locked loop, is currently applicable for dash. So option A is demodulation applications. Now in demodulation applications, you require the right frequency so that you can take the frequency of the carrier and then demodulate it. Option B is tracking a carrier or synchronizing signal. This is also an application. So here, both A and B are the applications. In communication circuits, PLL is currently applicable for both A and B options, demodulation applications also, and tracking a carrier or synchronizing a signal also, because we have to hunt for a correct frequency and then lock. So both these applications require that. So option C will be the right answer here, both A and B. So both A and B will be the right answer. Then question number 90. Basically, PLL, that is phase lock loop, is used to lock what? Is options are its output frequency, phase of the frequency, phase to the frequency, phase of the input signal, phase to the frequency, output frequency. Now, all these things are true. PLL is used to lock dash. All these things are true. It is used to lock dash its output frequency, it can lock phase of the frequency and phase of the input signal. So here the option D will be the right answer. All of the above will be the correct answer here. So here you can see option D will be the right answer, all of the above. Then we'll go to question number 91. A limiter circuit is also known as. Now, if you remember a clipper and clamper circuits, okay. So a limiter circuit is one which can limit the output waveform. It can clip the portion of the output waveform. So limiter circuit is also known as clipper circuit. So here option C will be the right answer, clipper circuit. So here you can see an example of series positive clipper. So the input is given here. This is your input to this circuit, and in that circuit you can see the output is one where the positive half cycles are clipped. These are clipped, these are not there, so it is called as positive clipper, and you get only the negative half cycles at the output. Now here the waveform at the output is limited to some point. It is whatever you want, you have clipped, and whatever you wanted to get as the output, you have got it as the output. So in that way, you can limit the waveform to some extent, to some portion. Okay, and that is why it is called as limiter. So here, a limiter circuit is also known as clipper circuit. Then question number 92, which of the following circuits is used to add a DC offset to waveform? So whenever you are adding a DC offset to a waveform, whether you are going to add it in a positive side or negative side, whether you are going to have positive clamping or negative clamping, so it is a clamper circuit. So which of the following circuits is used to add a DC offset to waveform is clamper circuit. So option A will be the right answer here, clamper. So here you can see a positive clamper circuit is shown, in which you are going to use a capacitor C, diode D, and a resistor R. Okay, this is the input voltage, and here you are having the output voltage. So this is the input voltage, and you can concentrate on this zero line here. So this is the zero line. Okay, now here in the output, if you see, zero line is here, zero line is here. So you have increased or added a DC offset voltage. So how much is the DC offset voltage added? Okay, so you are going to add a DC offset voltage, and this shift, this part of the waveform is going to shift on top, and then you can see that it has been shifted here and your zero line has come down. So it has gone up, it has gone up, and it is because you have added a DC offset voltage to the input. So it has gone above the zero line. Okay. So that is what is done in a clamper circuit. So which of the following circuits is used to add a DC offset to waveform? The option A is clamper circuit. Then question number 93, circuit used to shift the DC level of the input signal is. Again, the same question is asked here in another way. Circuit used to shift the DC level of the input signal. Again, if you're shifting the DC level of the input signal either on the positive side or on the negative side, then it is clamping only. So clamper is the circuit which will shift the DC level of the input signal. So option B will be the right answer here, clamper. A clamper will be the right answer. Then question number 94, a clamper circuit, number one, adds or subtracts a DC voltage to or from a waveform. So it is going to add or subtract a DC offset voltage. Either it is going to add and come up on the positive side, or it will subtract and go down on the negative side. Second point is, does not change the shape of the waveform. Yeah, it is not going to change the shape of the waveform. Shape of the waveform will remain same. Only the DC shift, either it will go on top or down. So which of the above statements is or are correct? So both the above statements are correct. So if you see the options, option A is one only, option B is second statement only, option C is both one and two, and option D is neither one nor two. So option C, both one and two statements are true, is the right answer. So here you can see the options as we have told. Now in this circuit, we have shown a positive clamper. So here a positive clamper means you are going to increase the DC offset. So here you can see this is the zero line, this is the zero line, and here you have got the zero line here. So you have gone on top. So there is a DC offset added and it has gone more positive. And you can see the shape of the waveform has not changed. Shape of the waveform is here same, and here also it has gone on top. It has been added with the DC level, but the shape of the waveform has not changed. So both the statements are true. So here you can see that option C is the right answer. Both 1 and 2 are the correct answer. Then question number 95, the primary function of a clamper circuit is. Options are suppress variations in signal voltage. Option B, raise the positive cycle of the signal. Option C, lower the negative cycle of the signal. Option D, introduce a DC level to an AC signal. So here, clamper, basically it is going to introduce a DC level to an AC signal. So option D will be the right answer. It will introduce a DC level to an AC signal. So here you can see option D is the answer for this question. Then question number 96. A clamper circuit uses diode only, or a transistors as and a resistors, or diode and transistors, or option D, diode, resistors and capacitors. So we have seen the clamper circuit earlier also. It uses diode, resistors and capacitors to do the clamping action. So option D will be the right answer. So here you can see you're going to use a capacitor, diode and resistor. So here you can see there is a capacitor, there is a diode and there is a resistor. So all the three are used to have a clamper circuit. The example of positive clamper is shown here. So here option D will be the right answer, diode, resistor and capacitor. Then question number 97, a circuit that removes positive and negative portions of waveform is called. So if your waveform is like this, and if you're going to remove the positive portion or the negative portion, if you're going to get output like this, or if you're going to get output like this, or if you're going to get a output like this, or if you're going to get an output like this. Okay, now all this is showing you that you're going to clip certain portion of the waveform at the output. From this input, you can get this output, you can get this output, you can get this output, you can get this output. So you're clipping, you're removing some portion. A circuit that removes positive or negative portions of waveform is called as clipper. So option B will be the right answer here, clipper. So option B is the right answer. Then question number 98. What type of diode circuit is used to clip off portions of signal voltages above or below certain levels? So the diode circuits what we have studied which clip off the portions are your clipper, and clippers are also called as limiters. So here option A will be the right answer, clipper or limiter. So clipper or limiter is the circuit, a diode circuit which is used to clip off portions of signal voltages above or below certain levels. Then question number 99. The circuit given in the figure is, so you can see this circuit, you are having one resistor, you are having a diode D1, you are having diode D2, and below the diodes you are having the voltages, the source of voltages. So these are there which can give you the biased flipping, and because you are having two diodes and both the diodes are going to work, one in positive and one in negative, so it will work on both the half cycles. Say for example, if you are having your input like this, so the output can be clipped and it is biased clipped, so output can be clipped like this, output can be clipped like this. So because it is going to clip on positive and negative side, it is called a dual clipper. So here the option C will be the right answer here, dual clipper. So here you can see the answer for this circuit is a dual clipper circuit. Then we'll go to the next question, question number 100. So what does the above diagram represent? So if you see the above diagram, the input is shown as a complete cycle, positive, negative half cycles. So here you can see positive, negative, positive, negative. And in output, you are having only negative half cycles. So the positive cycles are clipped. Positive cycles are clipped. Okay. So the options are positive series clipper, positive shunt clipper, negative series clipper, and negative shunt clipper. Because the positive cycles are clipped, the option C and D will be eliminated, and what remains will be positive series clipper and positive shunt clipper. Now in that also, if you see, this diode is in series with the load, so it becomes a positive series clipper. So this will be the right answer, positive series clipper, because in series the diode is in series with the load, and in shunt the diode will be parallel with the load. So if you have to see a positive shunt clipper, then the diagram will look like this. So here you can see the diode is in shunt with the load, or it is parallel with the load. So in series clipper, the diode is connected in series with the output load resistance. In shunt clipper, the diode is connected in parallel with the output load resistance. So here the option A will be the right answer. That is, it is the above shown diagram is positive series clipper. Thank you, students.